Greetings, friends. We'll start off with some induction today. The greatest discovery of them all, if you ask me, or almost anybody. We're going to start talking through about EMF, and then we're going to move into Faraday's law, induction, and finally energy stored in the B field. Okay, so let's get started. So here we are with our topics for this chapter, this unit, this section, this module. We do this one, and then we're going to have a little bit of time on some AC circuits because we'll be able to talk about inductance. So that's going to be that afterwards. Okay, so here we go. First thing I want to talk about is motional EMF. So what is motional EMF? Well, EMF does not stand for anything anymore. It used to stand for something called the electromotive force, which is not a particularly good name. And so they just said, okay, EMF, we'll keep the acronym, but it doesn't stand for that anymore. Okay. So what is the motional EMF? It's essentially the integration of the force per charge around a circuit loop. Okay, so EMF usually represented with the symbol script E, like that, is equal to the summed up force per charge around the loop. So essentially, and this is integrated around the loop. I don't really want to put anything there. D loop, DS maybe. Okay. Essentially what this is it's like the it's essentially like the work done. It's the, you see what happens here is that if you integrate the force per charge, if you examine the charge as a constant, the charge could like leave, and then you'd get 1 over the charge times the integration of FDS, and this is the work. Okay, this is the work done by the force. So this is basically something like the work done per charge. And there's a work done per charge. So what really is that? Well, it's kind of like a voltage, right? That means it's kind of like, what did the battery do, you know, as the charges went around a loop or something like that. So EMF essentially is EMF is essentially like a voltage of an ideal battery. So let me give you a clue as to how this works. Suppose I have a region of magnetic field here. Oops. No. Oh man, this computer. So suppose I have a region of magnetic field here. Okay. And inside this red box is a B field. Suppose that I'm sitting on the south pole of the B field, and or somewhere near it, and I'm looking, and the North Pole's over there. So the B field's going in. Okay. Now, in this B field, there is sitting a piece of wire. Like that. And it's some length long, some L or something. And I'm going to grab it, or I'm going to lasso it, and I'm going to pull it. Okay, so I'm going to grab it and pull it over here this way. I'm going to pull. And I'm going to try and pull, and I'm going to do work when I do that, okay? So what's going to happen to this conducting wire, which I will label. How about conducting rod? That's better. Conducting rod. Okay, so we're going to pull it to the right. So what's going to happen to the rod? Well, what's going to happen to the rod is you're going to think about, okay, well, wait a minute now. If I draw a slightly closer up picture, here's the rod. Okay, so here's the rod, and if it's moving off this way, I'm going to pull it this way, some force F. And that means it's going to start picking up, this is my pull, and it's going to start picking up some speed towards the right. Yeah. So it's going to start moving this way. And if it's moving that way, then we're going to look at it and say, well, wait a minute, I've got some charges with a velocity in a magnetic field. So they are going to feel force, right? So the force on the charges, if I think about the positive and negative charges, and suppose that they were just free to move around inside here, okay? So here's a positive charge, and here's a negative charge, okay? And I'm pulling it to the right. The force on the positive charge is Q, which is positive, times V cross B. So force on the plus charge is Q V cross B. And Q is positive, and V is to the right, and B is inwards. So it's fingers with the velocity this way. Fingers with the velocity this way, curl with the field that way into the page. For you, it looks like I'm curling at you, I guess, but it's for me, I'm curling into the page. And then the thumb would point force on the plus charge. So the force, the force on the plus charge must be going upwards. F on the plus charge is going upwards. Okay, so what that means is here these things are going to start going up here. I'm going to start noticing that there's a bunch of plus charges up here. As I pull this rod through the magnetic field, just grab it and pull it. It's going to accumulate some charge on one side. But what about the negative charges? What are the negative charges going to do? Probably nothing. I mean, what could they do? They're probably not going to do anything. Well, that's negative, and V cross B is once again V that way, and B is in, so V that way, cross B this way, but it's negative, so I got to turn it over. Oh, wait a minute. The force on the negative charge is downwards. Oh, all right. So if the force on the negative charge is downwards, I accumulated a bunch of positive charge on the top of the rod. I am going to accumulate a bunch of negative charge on the bottom of the rod down here. And here they are, negative, 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 negative. And so as I pull, the charges separate, and this goes to positive on this side, this goes to negative on this side, and it kind of starts looking like a battery, right? Now, if I pull harder, then what happens? Do I separate more charge? Well, probably because I'm going to increase the V. If I pull harder, the V is going to get a little bit bigger, right? And then the you're going to separate more charge, okay? So question there though is, can I just pull as much as I want? Is there anything to drag it or slow it down or do anything like that? Or is it just like free? I can just pull this thing, separate charges, and I get a battery for free. Hmm. It's like I'm doing some work to separate the charges. Yeah. So, but if it doesn't cost me very much, like if I can just however much pull, I can just pull as hard as I want, and I'll separate a bunch of charges, and then I'll just have a battery. Hmm. Well, if the charge is flowing up, that's like a current, right? If the positive charge is flowing up, negative charge flowing down, that's like a current in this wire. Yes, it's not a very big current, but imagine that the current is kind of going this way, right? I'm not even going to call it capital I. I'm going to call it little I, which is not very good, but it's a little tiny current. So, um, so the current is flowing upwards, which means that if I think about the IL cross B force on this thing, right? Force of IL cross B, then I is kind of going upwards, B is into the page, and there's a force backwards on this thing. Yeah. So there's going to be a kind of a resistive drag force on the thing. Okay. It is going to resist me pulling it, which makes sense, right? Because if there was going to be a force on it to resist me, it had better resist. Well, if there was going to be a force on it due to the magnetic field and the current, it had better resist me, because if it helped me, then all I would need to do is give it a little bit of a start, and then it would just take over and accelerate itself. And that would be like, I don't know, energy for free? That doesn't sound right. All right, so that's the start of motional EMF. You can create a battery in just a piece of conducting wire by pulling it through a magnetic field. Now what I'm going to do, I'm going to go back up to this diagram up here, and I'm going to connect um, this rod. I'm going to connect it. I'm going to say, all right, I'm going to take some wires. I'm going to run some wires off my battery here. Oops. All right, so it doesn't look like it connects, but I can assume it does. And I'm going to put a bulb over here, right, with some resistance R. And I'm going to pull the rod through the magnetic field, and I'm going to take that current. I'm going to connect these wires to it so that the current doesn't stop. I'm going to force the current to go through my resistor. I'm going to light that bulb up. I'm going to pull this thing through here. So essentially, I have established a delta V across this rod, right? Let's see here. Okay. The delta V. The delta V I've established across the rod. Well, think about this, right? All these positive charge up in the very top. All these positive charges in the very top um, are repelling further positive charges to come up there. But if I'm pulling hard enough, they'll go, right? Um, so I've established an electric field inside here, right? I've established an electric field inside here, which is pointing down in the rod, right? It's pointing that way. That way. That's my electric field, right? So my voltage is essentially E times L. If this length of if it's L here, all right? I know it's not exactly a parallel plate capacitor, but it's a good approximation at least. Okay, so what would be the voltage in terms of the B? So I have no way of measuring that E field. So what would be the voltage in terms of the B field? Well, you know that when I pull a rod and I have crossed fields, right? Because that electric field is starting to resist the motion of the positive charges upwards and the negative charges downwards, and it's encouraging them to go back the other way, right? So that means that if I pull the rod, what I'm going to do is I'm going to end up pulling at the cross fields speed, because the electric field is going to get established based on what speed I'm pulling it. So the cross fields E is going to be equal to VB, right? Because the forces are going to balance. I'm going to pull this thing through the magnetic field. That's going to start pushing plus charges up and minus charges downwards, and they're going to eventually reach a saturation. And the saturation is going to occur when the forces are balanced, right? There's a force from the B field causing the positive charges to go up. Now there's a force from the electric field causing them to go down. When those two are balanced, right, we get this condition of, right, QE equals QVB, right? And then we can cross off the Q's. And so what this means is that I could write the voltage as just equal to VB times L instead of E times L. Okay, so capital V is the potential difference in the rod, and little v is the velocity of the thing, right? Which is why I do this notation. Okay, so it acts like a battery. All right, so now I'm going to connect these two wires, and I'm going to say, all right, I'm going to cause the current to flow in the wires. I'm going to light the light bulb because my rod is acting a little bit like a battery, and that's essentially motional EMF. Okay, so what I did was I caused the rod to become like a battery, and it's because of its motion, and that's a motional EMF. Okay, it's basically like a voltage that shows up because you're pulling this thing through a magnetic field. Okay. All right. Now, when this was starting to get discovered, that it worked out, people weren't quite thinking of it this way, but this was when Maxwell, and by the way, these were kind of Faraday's ideas, right? And he did a couple of experiments at this time in 18, seems like yesterday, in 1820 or so, 1821, 22, around there, 1830, something like that. He did a series of experiments involving taking a coil of wire, right? Like this is a loop, this is a rectangular loop, but you could take a coil of wire. He took a coil of wire and he did kind of what we did in the lab, where you take the coil of wire and you move it in and out of the magnetic field. And then he took the magnet and he moved it so that the coil was stationary and the magnet moved. And then he kept the magnet stationary and moved the coil. And then he took the magnet away and then he replaced it with another coil, and he ran electricity through that coil and then kept another coil nearby and moved it in and out, and found that the same thing happened as if there was a magnet there. So he did these experiments over the course of about a year or two or 5 or something like that. And these were the ones that caused him to start really realizing that magnetism could cause the flow of electricity. All right. So at this point, this is where we've talked about electrostatics, which is motionless electric charges. Okay. Then we started talking about magnetostatics, which is currents flowing constantly. Okay. Now we're starting a current. If I take this thing and I accelerate it, now it's not static anymore. It's not a steady state situation anymore. It's a dynamic situation. Okay. So we're creating the voltage as we pull the thing around. So Maxwell came up with this idea because Faraday was, I don't know if you know much about Faraday. He never went to school. I don't know if I've talked very much about him. He never went to school. He was apprenticed at about age 10 or 11 to a bookbinder. He was from London. He was a low class Londoner, and I'm sorry, we don't have much time for in society for you people. And it's awfully a very tough job, old man. But off you go, into work you go. And he decided he didn't really like doing that, so he decided to go to the scientist of the day, whose name was Humphrey Davy, and ask if he could have a job as his lab assistant. And essentially, so Faraday knew he had no formal schooling. Okay. Um, but he became one of the most successful experimentalists ever in the history of physics, because of his methodical and precise experiments and his interpretations. He did his best, um, but they were very mechanical, right? He thought of what was happening. Maybe there's an invisible set of gears that are turning, and he couldn't really describe it I mean, he thought up the field idea, but Maxwell was the one who really took it and cast it into a form, and then actually Maxwell was the one who took it and cast it into a form involving the flux. But then Heaviside was really the one who put it in the form that we know them today. Oliver Heaviside was an electrical engineer, um, and so what we would say today is, look at this distance here, this distance s. The distance s is decreasing, right, at some rate, and the rate of s decreasing. Let's see if I can move over to a slightly less used side of things here. So the distance s is decreasing at the rate of v, right? In other words, d by dt, the rate of decrease of s, um, is v. Okay, so flux interpretation. Um, so what was I about to say? Oh yeah. So the flux. So what happens here is that if you look at the flux of B fields, let's take a snapshot of this. Let's take a snapshot of this and let's look at the flux of B through the area of the loop. But most of the loop is outside the B field as I've drawn it. So we can only look at the area of the loop that has the B field in it, which is that distance S. So flux of B through the loop. So the flux of B through the loop, we would have written it something like that, B dot dA. Okay, so B dot dA, well, B is a constant, right? I'm just sitting here and I'm not changing the magnetic field, so B is a constant, and now the area is changing. So the area of the loop is L high and S wide. So B times the area is equal to BLS. Okay. Now, what's essentially going on here is that if we think of the voltage that we got back over here, okay, and you think about the lab experiment. If you haven't watched the lab video, then you can watch that. What we need to find is if I just leave the loop there and I turn on the B field and everything's exactly as I see it there without the motion, then I don't get any current. I have to be pulling the thing through, right? I have to pull the loop. I have to grab and pull the loop. So something has to be changing. And what happens is that we establish a voltage by taking the time rate of change of the flux, right? So now what that means is I'm going to do d by dt of BLS. And lo and behold, the only thing that's changing here is not B and it's not L, it must be S. So the d by dt is going to comb through and find the thing that's changing, right? So this, in fact, is BLV, or if you like, VBL, and that's how you find your voltage, okay, via the flux method. So this gives rise to Faraday's law. All right, and Faraday's law, if we go back to day one, I'm not sure if that's, I think it was day one. I like to do this stuff on day one, so probably did. It's taken us this long to get to Faraday's law. All right. So Faraday's law essentially says that the circulation of E around a loop, right, around a curve, is going to equal the time rate of change of the flux of B through the surface that the loop makes. Is negative the time of the flux of B through surface, not just any old surface, it's the surface made by the curve, made by the loop, I mean, through surface made by loop. Okay, so in other words, the circulation of E around a loop. This is the first time we've talked about the circulation of E, but we've been talking about the circulation of B a lot. So this looks pretty much the same, except put the E instead of the B. So that's the circulation of E around the loop is equal to negative the time rate of change of the flux of B, right? So that's through a surface, and this is around a curve. All right. Okay, so that's what Faraday's law is. In other words, I cause a circulating E field when I change the flux of B through a loop. So take a look back. You know already that I started creating an E field, right? I started creating an E field inside this wire. As I connect that wire to the resistor with the other parallel wires over there, I'm going to find that that E field is pushing the current around the loop. Well, it would be going this way, I guess, right? The E field is pushing the current around the loop. So when I get that E field established, effectively, the thing that's doing the work is the electric field. It's pushing the charges. Okay. So we go back to here. All right, let's take a look at another example. All right, so that's Faraday's law. So let's take a look at another example of another kind of same type of thing, another moving rod in a magnetic field. So let's take a look here at this. Okay, so suppose that I have my resistor R here like this, and then I'm going to set some rails connecting the resistor like that, and then I'm gonna put a bar on this thing. This is essentially the same type of problem here. So if I take a bar and I stick the bar here, Okay. And I do the same thing. I'm going to pull the bar to the right. Oh, I need a magnetic field. Okay, I've got a big magnetic field everywhere in here. All right, and let's suppose that it's going to be going that way. Okay. So I have immersed this loop inside a magnetic field, and that's same as it was before going into the page. And I'm going to pull this bar um, off to the right. In fact, what I'll do is I'll just go ahead and instead of pulling it, let's do this. Let me give it a quick impulse. I'm going to give it a quick impulse, and I'm going to give it an initial velocity. Okay, so I'm going to give the bar an initial velocity, and it's going to slide on the rails. I'm going to give it basically an initial kinetic energy. Okay, and there we go. And we're going to kind of find out what happens here. Initial V naught means I have an initial kinetic energy. Okay. So the bar has some mass m to it. Okay. So as I push it, the same thing's going to happen, right? In the B field, there's going to be a push of charges, which are going to circulate. Well, right. If I think about what happened in the last example, I pushed the bar to the right and the charges went up. So the same thing can happen. If you look at force on the plus charges, the force on the plus charges is going to be V cross B up, right? So the plus charges are going up, which is going to lead to an I, which is circulating around in a counterclockwise direction in this case, right? So what's going to happen here is that the force from the magnetic field, or if you like, well, we'll talk about this too, I guess. The force from the magnetic field pushes the plus charges upwards. Okay, so a plus charge is going to go that way. And since these are conducting, it's going to go around like that. All right, so those are the plus charges. So this is my current I. All right, that's my current. Notice that the magnetic field, that makes a current loop, and notice that the magnetic field from that current loop, if I curl my fingers around with that current, I is kind of curly in a counterclockwise direction. And if I think about the thumb, which points the magnetic field from that current, it's pointing out of the page. So that sets up a magnetic field which is pointing out of the page. So this is like B, I'm going to call this BI to tell you that that's the magnetic field from the current. Okay. The red one is my magnet. I put that there. I have two poles of a magnet, one here and one behind the screen. And I have that and it's not changing and it's there. And I haven't done anything about that. I put it there and I'm not changing it. This one is due to the current that's kicked up in the rod and the circuit because of the motion of the rod through the magnetic field. Okay. So here I've got that. In this case, what's going to happen? Well, the force on the rod, okay, is going to be essentially I L cross B, right? This is the force on the rod because of the current in it. And which direction is that going to be? Well, current is going up and the magnetic field is in, so this force is to the left. Okay. Now recall that the voltage that we set up in that bar in the previous example, the voltage delta V in the bar or in the rod is equal to BLV. And in this case, it would be initially BLV naught, right? Well, I guess I shouldn't do that. Well, that's the initial voltage, and then it's going to change, right? Because the thing's going to slow down. I just gave it a push, and then I'm letting go, and it's going to, right? It's going to start, and then it's going to start moving at initial velocity V naught, and then it's going to slow down because there's a force on it. Okay, so the force on this thing is going to be backwards. Well, I mean to the left. Okay, there's a force on this thing that way. So V is getting lower and lower. So it's changing. So I'll just put a little function of time here, just to remind us that the V is a function of time, and therefore the potential is a function of time, and therefore the current is a function of time. Speaking of the current in this rod then is going to be delta V from the rod divided by R, because we'll assume that all the resistance is in that resistor there. All right, so that means that the force on this thing is equal to delta V over R times LB. And everything's perpendicular, so the cross product just becomes the sine of 90 degrees. So if I think about what the velocity is doing, I know it's slowing down, right? All right, so the velocity is slowing down because I gave it an initial push and there's a force backwards on it. So this is basically like a 4A problem, right? It's a 4A problem where I had a box sitting on a table and I pushed it, and it has an initial velocity and it's slowing down due to friction. Okay. Okay. There we go. Okay. So this is the force that is slowing the rod. Okay. So that means that the acceleration of the rod must be F over M, and that means it's basically this potential over R LB over M. This must be the acceleration of the rod, right? Acceleration is to the left. So the velocity of the thing as a function of time, this V of t, must be what it started at minus all of this shebang, right? The potential divided by R LB over M, all right? So that's what the times T, sorry. There, times T. So anyway, that looks like the acceleration term times time, and that's taking away from the initial velocity, okay? All right, so, okay. So let's examine what happens here to the initial kinetic energy of the thing, okay? So we know that it's gonna slide and then stop. The question is, though, what work has been done by the force, this FB, in slowing the rod? Well, if I take a look at that, okay, the force B, so I figured out what delta V over R looks like, right? I know what my delta V is. It's BL times little v divided by R times LB. Is that right? Yeah. Okay. Potential divided by R. So what the force looks like now is just I got this L and B that I can square. So it looks like BL over R times V. Okay, so that's the force that this thing is exerting. How much work does this force do? How much work is done by this force F? Well, in order to do that, this force is changing as the rod slows down, right? Because it's a velocity dependent force. So the force is changing, and if I want to know what the work done is, the work done is going to have to be essentially F dot ds, but this is not around a loop. We've been using dot ds as a circulation, but this is just a straight, maybe I should call it dx or something like that. So it's horizontal only. Okay. Okay, so I can look at how much work is getting done by the force F. And in fact, if I want to be a bit clever about this, and who doesn't want to do that? I know that there's an expression for power generated as a current flows through a resistor. Okay, but the power and the work done aren't the same thing. So if I really want to get the power, what I would need to do, if I want to compare the power, because in an electrical circuit, we know the power, right? We talked about power dissipated in a resistor as being equal to I squared R or delta V squared over R or something like that. So if I want the power so I can compare, I'm going to have to take d by dt of the work done. Right? So the work done is that integral right there. And if I take d by dt of that, come on. Okay, there we go. Essentially what that means is I can take the integral, a little bit of a cheat here, but I can take the derivative and just slide it through onto the dx here so that it looks like f dot v. In other words, I take the d by dt and stick it over here on the dx, so it becomes dx by dt, and it's f dot v. All right, so that means that the power, if I look at this expression for the f, and then I put a v on there, it's going to be, the work done is, that's just going to square the v, right? Now I get the v squared divided by r. Okay, but now go back and take a look here and compare, where did that energy go? So that's the work done. That decreases the kinetic energy of the rod. Take a look at the power dissipated in the resistor. Okay, let's take a look at that, because the energy had to have gone somewhere, right? The energy, the kinetic energy that I had in the rod got taken away by this work, all right? But it couldn't have just gone out into nothingness, right? We already know that energy has to be conserved. So if I look at the potential squared divided by R, I know the potential is BLV, and I got to square it over R. Look at that. So the energy that I had in the rod has turned into electrical energy. I had mechanical energy in the rod. I had mechanical energy in the rod. The force of the B field did work. Well, actually, it didn't. The electric, well, anyway, the force, that force of the current on the current through the rod did work to cause the rod to slow down, which took away the kinetic energy, but then caused the current to flow, and all of the energy that you saw initially mechanically in the rod has now become electrical energy dissipated in the resistor. This is the real big deal here, okay? It's that you can take mechanical energy like that and turn it into electrical energy, and this was the big thing that Faraday's law kind of concludes for you is that if I put work in as a mechanical input and I put in kinetic energy, whether it be linear or rotational, which we'll do in a little while, um, I can convert that into electrical energy and I can light a light bulb with it. All right. And that was the big thing that Faraday's law gives us. This is essentially the principle by which every single energy electrical power plant works, right? There's some mechanical energy input, right? Usually due to some thermal burning of something, right? It's not a bunch of elves sitting there pulling rods or rotating the rods around, right? So that the loops around so that you get the mechanical energy. You have to have some combustion, which causes something to spin, right? And then you take the spinning and you force it into, you push it past a magnet and it becomes electrical energy and you just ship it out to everybody. Okay. So this is essentially the principle. Faraday's law is the principle by which electrical energy is generated, and it was because of this uh, that um, this became pretty much one of the most useful things uh, that we have. Becomes electrical energy. All right, so that's the conversion, and that's what Faraday's law told us. Right? Okay. So that was the whole point of that example, was to show that that initial kinetic energy um, decreased. There was work done by a force, and that showed up as electrical power. All right, so in a little while, I'll do the rotating loop example, and we'll do a couple of more examples of flux changes through loops. But that's its start. That's your beginning start on Faraday's law, and like I said, probably the most important of all four. Of course, you couldn't have had that one without the other three. So, I mean, okay, sure. But, anyways, enjoy a wonderful magnetic day. Thinking about whenever you turn lights on or turn your computer on, your electrical energy has come from some type of loop or some type of flux change in a magnetic field. Happy day, friends.